September 18th, 1942. The ways of the Bethlehem Fairfield Shipyard in Baltimore, Maryland, trembled as 5,000 rivets held back 14,000 tons of welded steel. The SS Patrick Henry sat completed, ready for launch. She was the first of a new class of cargo vessel that would either save the Allied war effort or prove to be the most catastrophic industrial miscalculation in American history. Henry Kaiser stood on the platform, watching his revolution take physical form. 70 days earlier, this ship had been nothing but blueprints and raw steel plates. Traditional shipbuilding wisdom said a cargo vessel required 8 to 12 months from keel laying to launch. Kaiser had promised to do it in 70 days. The maritime establishment had laughed at him. The man had built dams and highways, but he'd never constructed a ship in his life. Now the Patrick Henry sat before them, fully functional, ready to carry 10,000 tons of cargo across submarine-infested waters to keep Britain fighting. But as champagne shattered against her bow and the crowd cheered, naval architects in the back of the crowd exchanged worried glances. They'd seen the construction methods. They knew what compromises had been made in the name of speed. This ship, and the hundreds like her already under construction, might not survive their first winter crossing of the North Atlantic. The mathematics of maritime warfare in 1942 were brutally simple and utterly terrifying. German U-boats were sinking Allied merchant ships faster than shipyards could replace them. In 1942 alone, U-boats sent over 8 million tons of Allied shipping to the bottom of the Atlantic. Each merchant ship carried food, fuel, ammunition, aircraft, tanks, everything Britain needed to survive, and everything America needed to build an invasion force in England. Admiral Karl Dönitz, commander of Germany's U-boat fleet, understood the equation perfectly. Sink ships faster than the Allies can build them, and Britain starves. Britain falls. The war ends. Germany wins. By the spring of 1942, Dönitz was winning that equation. His wolf packs were destroying ships at a rate that made Allied victory mathematically impossible. The British Admiralty calculated that at current loss rates, combined with reduced construction from bomb-damaged British shipyards, the merchant fleet would be unable to maintain supply lines by mid-1943. The United States Maritime Commission faced an impossible requirement: build hundreds of cargo ships, build them immediately, build them with a shipbuilding industry that had nearly vanished during the Depression years. In 1939, American shipyards employed fewer than 50,000 workers and delivered perhaps 100 ships per year. The Commission needed thousands of ships within 2 years, built by workers who'd never held a welding torch or read a ship's blueprint. Traditional shipbuilding methods could not meet this demand. Each vessel was essentially a custom product, built piece by skilled craftsmen who understood how to shape steel plates, drive rivets, and fit complex systems into hulls. A single cargo ship might require 800,000 to 1 million rivets, each one heated red-hot and driven by skilled riveters working in teams. The process was labor-intensive, time-consuming, and required expertise that took years to develop. America did not have years. Britain had months. Henry Kaiser proposed something that marine architects considered either brilliant or insane, possibly both. Build ships like automobiles, mass production, interchangeable parts, assembly line techniques, prefabricated sections, and most controversially, welding instead of riveting. The proposal violated every principle of traditional shipbuilding. Ships were not cars. They operated in conditions that automobiles never faced. Salt, water, heavy seas, cargo loads that flexed the hull with every wave, temperature extremes from Arctic convoys to tropical waters. Riveted construction had proven itself over centuries. The overlapping plates and mechanical fasteners created structures that could absorb stress, survive damage, and last for decades. Welding was faster, required less skilled labor, and eliminated the need for thousands of rivet holes that weakened plates. But welded ships were continuous structures. A crack that started in one plate could run through hundreds of feet of welded seams without stopping. Riveted seams acted as natural crack arresters. Welded seams did not. The Maritime Commission approved Kaiser's plan anyway. They had no choice. The alternative was losing the war. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. In January 1941, the Commission selected a proven, British design, the Ocean-class tramp steamer, as the foundation for what would become the Liberty ship. The British had developed these simple, rugged cargo vessels for emergency wartime construction. They weren't fast, they weren't elegant. They were functional, with a single steam engine, basic cargo handling equipment, and a design optimized for rapid construction using traditional methods. American engineers adapted the British plans for welding and mass production. The hull was simplified further. Complex curves were replaced with flat plates and simple angles. The design eliminated features that required skilled labor or slowed construction. What emerged was arguably the most basic merchant ship that could still safely cross an ocean. 441 feet long, 57 feet wide, displacing 14,000 tons when fully loaded. A single triple expansion steam engine produced 2,500 horsepower, driving the ship at 11 knots, barely faster than walking speed. 5 cargo holds could carry 10,700 tons of tanks, trucks, locomotives, aircraft, ammunition, food, anything the war effort needed. Defensive armament included a 3-inch gun on the stern, a variety of machine guns, and gun crews from the Navy Armed Guard. The crew quarters were Spartan, the navigation equipment basic, the entire vessel stripped of anything that wasn't absolutely essential. These were emergency ships, designed to make perhaps a single voyage across the Atlantic before German torpedoes found them. If they lasted longer, that was a bonus. Construction began at a pace that seemed impossible. Richmond Shipyard No. 1 in California, one of Kaiser's facilities, laid the keel of its first Liberty ship on April 14, 1941. By September, the yard had delivered 5 ships. By the end of 1941, 18 Liberty ships had been completed across all American yards. Then Pearl Harbor transformed urgency into desperation. President Roosevelt addressed the nation in January 1942, declaring that America would build 8 million tons of merchant shipping in 1942 and 10 million tons in 1943. The numbers seemed absurd. Total American shipbuilding in 1941 had been less than 1 million tons. Roosevelt was demanding a 10-fold increase in a single year. The Liberty ship program became the vehicle for that impossible goal. Kaiser's Richmond yards expanded explosively. Richmond Shipyard No. 2 opened in January 1942. By year's end, Kaiser operated 4 complete shipyards in Richmond alone, employing over 90,000 workers. The yards ran 3 shifts, 24 hours a day, 7 days a week. The workers came from everywhere: farm laborers, housewives, retired mechanics, teenagers who'd never seen the ocean, all of them trained in weeks to do jobs that traditionally required years of apprenticeship. Rosie the Riveter became the face of this industrial army, though the name was misleading. These workers were welders now, not riveters. They learned to strike arcs, run straight beads, and join steel plates in crash courses that lasted days or weeks. The training was necessarily superficial. There was no time to teach metallurgy, stress analysis, or the subtle skills that master welders developed over careers. Learn to make a sound weld, practice on scrap until you can do it consistently, then get on the production line. The prefabrication revolution transformed shipbuilding from craft to industry. Rather than constructing each ship as a unique assembly, Kaiser's engineers broke Liberty ships into large sections that could be built separately, then joined together on the building ways. Bow sections, stern sections, midship sections, deck houses, all fabricated in dedicated shops away from the congestion of the ways. Workers could build these sections at ground level, in controlled conditions, with proper lighting and access. No more working on scaffolding inside cramped hulls. No more welding overhead in impossible positions. The sections moved through fabrication shops like car bodies through Detroit assembly plants. Workers at each station performed specific tasks, then the section moved to the next station, By the time a section reached the building ways, it was essentially complete, needing only to be lifted into position and welded to adjacent sections. The scale of the operation defied belief. A complete Liberty ship consisted of roughly 250,000 separate parts. The hull alone required approximately 30,000 welded joints. Each joint had to be executed correctly, or the ship would leak, crack, or fail catastrophically under stress. Quality control in traditional shipbuilding relied on the expertise of master shipwrights, who could spot problems through experience and intuition. Kaiser's yards relied on inspection procedures, measurement, protocols, and testing systems designed to catch errors that inexperienced workers inevitably made. The results were immediate and impressive. Construction times dropped from 70 days to 60 days to 50 days. Kaiser's Richmond Yard No. 2 established new records repeatedly. The yard became a competition with itself, each Liberty ship built faster than the last. In November 1942, Richmond launched the SS Robert E. Peary just 4 days and 15.5 hours after her keel was laid. The achievement made headlines worldwide. Newsreels showed the incredible feat, a complete ocean-going cargo ship assembled in less than a week. The propaganda value was immense. America's industrial might, unleashed and unstoppable, building ships faster than Germany could sink them. Admiral Dönitz read the reports from America and understood what they meant. His U-boats would have to sink not just the existing Allied merchant fleet, but an endless stream of replacements, pouring from American yards at impossible speeds. The mathematics of maritime warfare were shifting, but Dönitz didn't know yet that American mass production had introduced a fatal flaw into those thousands of ships racing toward the Atlantic. The Liberty ships started breaking in the winter of 1942 and 1943, and they broke in ways that terrified everyone who understood what was happening. Continuing Part 1. The SS Schenectady sat at the fitting-out dock in Portland, Oregon, on January 16, 1943. She was brand new, launched barely 2 months earlier from Kaiser's Swan Island yard. The morning was calm, the harbour water still, the temperature 28 degrees Fahrenheit. No storm threatened. No enemy action endangered the vessel. Then, without warning, a sharp crack echoed across the quiet harbour. Within seconds, the entire ship fractured completely in two. The hull split from deck to keel as if sliced by an invisible blade. Dock workers watched in horror as the bow and stern sections sagged in opposite directions, the ship's back broken while safely tied to the pier. The Schenectady hadn't hit a mine. She hadn't been torpedoed. She hadn't even left port. She had simply broken apart while sitting still in calm water on a cold morning. The Schenectady was not alone. That same winter, catastrophic failures struck Liberty ships across both oceans. The SS John P. Gaines broke completely in half in calm seas off the Aleutian Islands. The SS SO Manhattan, a two-tanker built using identical welding methods, cracked so severely her crew abandoned ship in panic, convinced she was about to split apart. Between 1942 and 1944, more than 1,500 Liberty ships reported serious structural cracks. At least 19 vessels broke completely in half. 3 ships, the SS Benjamin Chew, SS Montana, and SS William H. Welch, simply vanished at sea without sending distress signals, disintegrating so rapidly their crews had no time to radio for help. These weren't war casualties. These ships were committing suicide. The Maritime Commission convened emergency investigations. Naval architects, metallurgists, and marine engineers descended on shipyards and examined fractured hulls. What they found was terrifying in its implications. The cracks typically initiated at stress concentration points, square corners of cargo hatches, gun mounts, abrupt changes in plate thickness. Once a crack started, it propagated through the welded hull plates at extraordinary speed. Some fractures raced the entire length of a ship in seconds, unzipping the hull from bow to stern before bulkheads or structural frames could arrest the failure. The technical term was brittle fracture, but the reality was simpler and more frightening. The steel was shattering like glass. Naval architects understood ductile failure, where metal bends and deforms under stress, providing visible warning before final collapse. They understood fatigue failure, where repeated stress cycles gradually weaken material over time. Brittle fracture was different. No warning, no gradual deformation, just sudden, catastrophic collapse that consumed entire ships in seconds. The steel itself met all specifications. Laboratory tests showed proper chemical composition, adequate tensile strength, and appropriate hardness. The welds looked sound under visual inspection and X-ray examination. The designs came directly from proven British blueprints that had produced thousands of reliable ships. Yet Liberty ships were fracturing spontaneously in conditions that should have been routine. The investigations discovered a troubling pattern. Most failures occurred in cold weather, when water temperatures dropped below 40 degrees Fahrenheit. The North Atlantic in winter, the Bering Sea, the Arctic convoy routes to Murmansk, all became killing grounds for Liberty ships. But traditional riveted ships operating in the same conditions, facing the same seas and temperatures, were not breaking apart. The difference had to be the welding. Metallurgists examined failed sections under microscopes, searching for clues in the fractured steel's crystalline structure. They found that the steel underwent a fundamental transformation at low temperatures. Above roughly 40 degrees, the steel remained ductile, capable of absorbing stress by deforming slightly. Below that temperature, the steel's behavior changed. It became brittle, losing the flexibility that normally prevented cracks from propagating. The welding process itself was creating problems that designers had never anticipated. When a welder runs a torch along a seam, the localized temperature exceeds 2500 degrees Fahrenheit. The metal expands dramatically in that heat zone. As the weld cools, it contracts, but the surrounding cold steel constrains that contraction, creating residual tensile stress locked permanently into the structure. Every weld in a Liberty ship carried these internal stresses. Thousands of welds meant thousands of points where the steel was under tension, even before the ship faced its first wave. The construction sequence made everything worse. Welders typically started at the edges of plates and worked inward, or began at one end of a long seam and ran straight to the other end. Each cooling weld pulled and warped the plates. The stress built and concentrated. When welders finished one section and moved to the next, they were locking that accumulated stress into the structure permanently. The squared-off design of Liberty ships compounded the problem. British marine architects had specified those hard right-angle corners at hatch openings for easier cargo loading. Nobody had considered that sharp internal corners create stress concentrations that multiply applied loads by enormous factors. Engineering calculations showed that a 90-degree corner could create stress multipliers of 3 to 4 times the nominal hull stress. Every wave that flexed the hull sent stress spikes through those corners. Combined with residual welding stress and brittle steel, those corners became crack initiation sites waiting for the right conditions to fail catastrophically. The continuous welded structure meant that once a crack started, nothing would stop it. In riveted ships, cracks hit riveted seams and stopped. The overlapping plates and mechanical fasteners created natural crack arresters. Welded Liberty ships had no such protection. A crack in one plate could run unimpeded through hundreds of feet of continuously welded seams. The efficiency that made welded ships faster to build also made them vulnerable to failures that riveted ships couldn't experience. Henry Kaiser faced a nightmare scenario. His yards were launching Liberty ships at record rates, but those ships were developing a reputation among merchant mariners as death traps. Sailors reported constant anxiety serving aboard Liberty ships, especially in cold weather. Every groan of the hull might signal impending fracture. Sleep was difficult when the ship beneath you might unzip without warning in freezing Atlantic waters. Some experienced merchant mariners refused to ship out on certain Liberty ships with known cracking histories. Insurance companies raised premiums. The British Admiralty quietly questioned whether American ships should be allowed in Arctic convoys. But the ships were desperately needed. U-boats were still sinking Allied merchants faster than replacements arrived. The invasion of Europe, still more than a year away, would require the largest amphibious logistics operation in human history. Every cargo ship mattered, even ships that might break apart. The solution came from an unexpected source, not from the naval architects or metallurgists conducting official investigations, but from a welder working the night shift at Kaiser's Richmond Yard No. 3. Bessie Hamill had been welding hull sections for 8 months, long enough to notice something the engineers apparently hadn't. Bessie Hamill was one of thousands of women who had flooded into shipyard work after the men shipped overseas. She had no engineering degree, no formal training in metallurgy or stress analysis. She simply watched steel move under her torch every night and recognized patterns that the college-educated engineers were missing. Every night, Hamill watched her welding team join massive steel plates in sequences that made no mechanical sense. Welders started at the edges of plates and worked inward, or began at one end of a long seam and ran straight to the other end. As each weld cooled, the metal contracted, pulling and warping the plates. She could see the stress building, watch the steel distorting under her torch. When welders finished one section and moved to the next, they were effectively locking that stress into the structure permanently. It was like tightening the center bolts on a car wheel before securing the outer ones, a recipe for imbalance and failure. Hamill understood instinctively what the engineers were discovering through complex calculations. The sequence mattered. Where you started welding, and in what order you completed the joints, determined how stress distributed through the structure. Her foreman dismissed her concerns initially. She was a welder, not an engineer. The welding sequences came from the engineering department, from men with college degrees and naval architecture training. Who was she to question their expertise? Hamill persisted anyway. In November 1943, she requested a meeting with yard supervisors, breaking chain-of-command protocols that could have gotten her fired. She brought samples with her, test plates she had welded on her own time using different sequences. Some plates, welded using the standard production sequence, showed significant warping and visible stress patterns. Other plates, welded from the center outward in carefully planned sequences, lay flat and true with minimal distortion. The difference was visible to anyone who looked. One supervisor agreed to observe the production line during Hamill's shift. What he saw confirmed her observations in real time. Welders were essentially torturing the steel, forcing it to accept stresses it would carry for its entire service life. Every cooling weld created residual tension in the metal. The standard construction sequence meant these internal stresses accumulated and concentrated at specific points, particularly at the corners of hatch openings and other stress concentration areas. When those ships hit cold North Atlantic water, the steel became brittle. The locked-in residual stress, combined with brittleness, created perfect conditions for catastrophic fracture. Hamill's insight was elegantly simple. Weld from the center of sections outward, allowing stress to dissipate toward the edges rather than concentrate in the middle. Alternate welding locations to prevent heat buildup in any single area. Never complete long continuous welds in single runs. Instead, use a balanced sequence that distributed cooling stresses evenly across the structure. These were not revolutionary metallurgical theories requiring advanced mathematics. They were practical observations from someone who actually worked with the material every day, who felt the metal move under her torch and recognized the consequences. By December 1943, Hamill's observations reached Henry Kaiser himself. He faced a brutal choice that would define both his reputation and potentially the outcome of the war. The Liberty ship program was already under intense congressional scrutiny for the cracking epidemic. Admitting that the construction sequence, not the steel quality or weld integrity, was the fundamental problem meant acknowledging that every ship built so far had systematic flaws baked into their hulls. It meant temporarily slowing production to retrain thousands of welders. It meant redesigning the entire assembly process at every shipyard in America. It meant admitting that a night shift welder with no formal education had identified a critical flaw that the entire engineering establishment had missed. but it also meant potentially solving the fracture crisis that threatened to undermine America's entire maritime logistics chain and hand victory in the Battle of the Atlantic to Admiral Dönitz's U-boats. Kaiser, to his credit, did not hesitate. He authorized immediate testing of Hamel's theories, pulling entire hull sections from the production line for experimental reconstruction. The metallurgists and engineers who had spent months analyzing failed ships through laboratory testing and theoretical calculations were now taking instruction from a night shift welder who had never seen the inside of a college classroom. The test results were damning and revelatory in equal measure. When Kaiser's metallurgists examined hull sections constructed using conventional sequences versus Hamel's methods, the difference was measurable and dramatic. Residual stress gauges showed traditional welds carried internal tensions exceeding 30,000 pounds per square inch, concentrated at key structural points. Hamel's sequenced sections distributed those stresses across broader areas, with peak readings barely reaching 12,000 pounds per square inch. The steel itself was identical. The welds were chemically indistinguishable. The designs were the same, only the order of operations had changed. Yet the structural integrity improved by factors the engineers initially refused to believe, until repeated testing confirmed the results. The physics behind the failures finally became clear in a way that made perfect, terrible sense. Steel is not a static material. It is a crystalline structure that responds dynamically to temperature changes. When welders run a torch along a prythes seam, they create a localized temperature exceeding 2,500 degrees Fahrenheit. The metal expands dramatically in that heat zone. As the weld cools, it contracts, but the surrounding cold steel constrains that contraction. The result is residual tensile stress locked permanently into the structure unless the welding sequence allows the stress to redistribute naturally. Liberty ships were suffering from what metallurgists called brittle fracture propagation. The steel used in their hulls, a basic carbon steel designated as shipbuilding grade, performed adequately in warm water, but it underwent a critical transformation in the North Atlantic's near-freezing temperatures. Below roughly 40 degrees Fahrenheit, the steel's ductility collapsed. Normally, metal absorbs stress by deforming slightly, bending rather than breaking. Cold steel loses that flexibility. It becomes brittle, more like glass than the tough material welders worked with in California's mild shipyards. When brittle steel meets concentrated residual stress at a sharp corner, say the square edge of a cargo hatch, physics takes over with brutal efficiency. A microscopic crack initiates. In ductile steel, that crack would stop, absorbed by the material's ability to yield. In brittle steel under tension, the crack becomes a sprinting fracture. The energy stored in those residual stresses provides fuel for the crack to propagate. Sharp corners act as stress concentrators, multiplying local stress by factors of 3 or more. The crack accelerates, sometimes exceeding the speed of sound in steel, racing through the hull before bulkheads or frames can arrest it. The SS Schenectady's fracture made perfect sense in hindsight. She had been built in early winter, welded in sequences that maximized residual stress. Her hull carried millions of pounds of locked-in tension. When the Portland morning dropped to 28 degrees, the steel became brittle. The stress concentration at a hatch corner initiated a crack. That crack found a straight path through continuously welded deck plates. No riveted seams to slow it, no stress relief brakes to stop it. The fracture consumed the ship in seconds, releasing decades' worth of stored energy in one catastrophic failure. The solution was clear, but implementing it would require transforming every aspect of Liberty ship construction. In January 1944, Kaiser made decisions that would either vindicate his industrial revolution or expose him as a reckless profiteer who had sent thousands of sailors to sea in defective ships. He ordered comprehensive modifications to all Liberty ship construction procedures. More importantly, he began designing an entirely new class of vessel that would incorporate every lesson learned from Liberty ship failures. The Victory ship program represented a complete rethinking of emergency cargo vessel design. These would not be simple modifications to existing Liberty ships. They would be fundamentally different vessels, built around Bessie Hamill's welding observations and the hard-earned lessons written in fractured hulls across two oceans. The gamble was staggering. Liberty ships were still desperately needed. U-boats had sent over 2,500 Allied merchant vessels to the bottom since 1939. The invasion of Europe, still months away in early 1944, would require unprecedented logistics. Every ship mattered, yet Kaiser was betting he could implement Hamill's sequenced welding system, redesign hull structures to eliminate stress concentrations, improve steel specifications, and somehow maintain production speeds that already seemed miraculous. His competitors thought he had lost his mind. Congressional investigators sharpened their knives, ready to crucify him if production collapsed. British Admiralty officials expressed polite skepticism that bordered on open mockery. Kaiser's engineers worked backward from every failure point. Every square corner in the Liberty design was replaced with rounded transitions. The hatch openings that had birthed so many catastrophic cracks were redesigned with generous radiuses, eliminating the stress multipliers that turned normal loads into fracture initiators. The deck and hull plate thicknesses were recalculated, not simply to add strength, but to ensure stress distribution matched the new welding sequences. Structural frames were repositioned to align with natural stress relief points rather than fighting against the welding patterns. The steel itself changed. Kaiser's metallurgists specified a new alloy designation with dramatically improved low-temperature toughness. The carbon content was reduced slightly. Manganese content was increased. Small additions of nickel, expensive and rationed for armor plate production, were justified by demonstrating that just 0.25% nickel content dramatically improved the steel's resistance to brittle fracture at low temperatures. The Maritime Commission initially balked at the cost until Kaiser presented calculations showing that preventing a single ship loss would pay for the upgraded steel in 50 vessels. In March 1944, the new steel specification was approved for all future construction. Then came the massive undertaking of retraining the entire workforce. Richmond Shipyards alone employed over 90,000 workers by early 1944. Thousands were welders who had learned their trade in weeks-long crash courses, mastering just enough technique to lay straight beads at production speed. Now they needed to understand sequencing, stress relief, and thermal management. Kaiser established welding schools within the yards themselves, pulling experienced welders like Bessie Hamill off the production lines to teach. Every welder received numbered sequence cards for each hull section. Weld number 1 here, number 2 there, never deviating from the prescribed order. The sequences were not suggestions. They were absolute requirements backed by the authority to fire any welder who skipped steps or improvised. The prefabrication system expanded dramatically. Rather than welding large sections on the building ways where sequencing was difficult to control, Kaiser's planners broke Victory ships into smaller modules constructed in dedicated shops. A bow section might contain 50 separate prefabricated assemblies, each welded in controlled conditions using optimal sequences, then stress-relieved in heating ovens before final assembly. This modular approach meant welders could work from the center of each small section outward, exactly as Hamill had demonstrated, without the constraints of assembling a full hull on the ways. The stress relief ovens themselves represented a significant investment. Massive structures capable of heating steel sections to 1100 degrees Fahrenheit and slowly cooling them allowed the metal's crystalline structure to relax, dissipating residual stresses before they accumulated to dangerous levels. Every major structural component passed through these ovens before final assembly. The additional time and cost were justified by one simple fact: Victory ships were not breaking apart. The skeptics had ammunition when the first Victory ship keels were laid in February 1944. Construction took significantly longer than Liberty ship records. The propaganda machine's miracle of 4-day construction was not repeated. Critics declared the program a failure, proof that quality and speed were incompatible. Kaiser ignored them. He was watching crack inspection reports, not just construction times. The first Victory ships showed 0 stress cracks in post-construction inspection, not reduced cracks. 0. The steel arrived pre-cut and pre-formed from rolling mills that had retooled specifically for Victory ship production. Unlike Liberty ships, where yard workers cut and shaped plates on site, Victory ship components arrived ready for immediate assembly. Curved bow sections came pre-formed to exact specifications. Deck plates had pre-drilled bolt holes for temporary alignment. Frame sections were pre-welded assemblies. This preparation work, done in controlled factory environments, eliminated variables and ensured consistency across thousands of components. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Assembly on the building ways followed a radically different sequence than Liberty ship construction. Instead of starting at the keel and building upward, Victory ships were assembled in large modules that came together almost simultaneously. The engine room section, the cargo hold sections, the bow and stern, all were constructed in parallel, then lifted by massive gantry cranes and positioned in single coordinated operations. On May 12, 1944, Richmond Yard No. 2 executed its most ambitious assembly yet. 17 major modules representing 85% of a complete hull were positioned and aligned in just 11 hours. Welders then connected these modules using the same center-outward sequences, but now they were joining stress-relieved sections rather than building stressed sections from scratch. The production timeline stabilized at speeds that, while not matching Liberty ship records, remained extraordinary by any traditional shipbuilding standard. Victory ships were being completed in an average of 60 days from keel laying to sea trials. More importantly, they were surviving. The first Victory ships entered service in the spring of 1944, just in time for the massive logistics requirements of the Normandy invasion. Meanwhile, Liberty ship construction continued with modified procedures. Existing Liberty ships received reinforcing modifications. Steel straps were welded across stress, concentration points. Riveted crack arrestor straps were installed at intervals along deck seams. Hundreds of Liberty ships already in service were recalled for these modifications. The work was expensive and time-consuming, but necessary. Too many ships had broken. Too many sailors had died in ships that split apart in cold seas. The production numbers told a story of American industrial capacity that the world had never seen. In 1942, American shipyards delivered 746 Liberty ships, totaling 8.2 million tons. In 1943, production peaked at 1,949 Liberty ships. By the program's end in 1945, American yards had delivered 2,710 Liberty ships, 2,710 cargo vessels in less than 4 years. At peak production, Liberty ships were being delivered at a rate of 3 per day. 3 complete ocean-going cargo ships every single day. The numbers defied comprehension. Germany's entire U-boat construction program, which had begun years before America entered the war, produced approximately 1,100 U-boats between 1935 and 1945. 10 years of German submarine construction produced fewer vessels than American Liberty shipyards delivered in 3 years. The mathematics that Admiral Donitz had relied upon, sink ships faster than the Allies can build them, had been obliterated by American industrial capacity. By late 1944, U-boats were still sinking Allied merchants, but the losses no longer mattered strategically. For every ship the U-boats sent to the bottom, 3 new ships arrived from American yards. The wolf packs could not win a war of attrition against an enemy that could replace losses faster than they could inflict them. The Battle of the Atlantic, the longest continuous military campaign of World War II, was effectively decided not by naval tactics or technology, but by shipyard workers in California, Oregon, Maine, and Maryland, who learned to weld steel plates in the correct sequence. Victory ships proved their worth in the war's final year. Between June 1944 and August 1945, 531 Victory ships entered service. Not a single one suffered catastrophic hull failure. Minor cracks appeared in a handful of vessels, stress concentrations that inspection caught before they propagated. These cracks were repaired using the same stress relief welding procedures that Hamill had pioneered, and the ships returned to service. The contrast with Liberty ships was absolute. Liberty ships had a failure rate of approximately 4.6%, meaning 1 in every 22. Liberty ships suffered catastrophic structural failure during its service life. Victory ships had a failure rate of 0%. The additional cost of Victory ship construction, approximately 30% more expensive than Liberty ships, was recovered within months through eliminated losses and reduced insurance premiums. The human cost of the Liberty ship failures, while overshadowed by combat casualties, was significant. Approximately 300 sailors died in Liberty ship structural failures, men who drowned not because of enemy action, but because the ships beneath them fractured in cold seas. The exact number remains uncertain because some ships simply vanished, their final moments unrecorded. The SS Benjamin Chew disappeared in February 1944 with all 44 crew members. The SS Montana vanished in January 1944 with 40 crew. The SS William H. Welch disappeared in March 1944 with 55 crew. These ships sent no distress signals. They simply ceased to exist, almost certainly victims of catastrophic brittle fracture that consumed the vessels faster than crews could react. Victory ships eliminated these losses. Merchant mariners who transferred from Liberty ships to Victory vessels reported dramatically improved confidence. Sleep was possible again. The constant anxiety that the hull might unzip without warning disappeared. Crews pushed Victory ships harder because the ships could take the punishment. That confidence translated to mission effectiveness, faster turnarounds in port, willingness to sail in marginal weather, aggressive maneuvering when under attack. The economic calculation was brutal but clear. A Liberty ship cost approximately $2 million to build. Victory ships cost $2.6 million, a 30% premium. But Liberty ships had a 4.6% chance of catastrophic failure. Those failures killed an average of 18 crew per incident and destroyed cargo worth 3 to 5 times the ship's construction cost. Victory ships' zero failure rate meant the additional $600,000 in construction cost was recovered within months through eliminated risk alone. The legacy of the Liberty ship program extended far beyond the immediate wartime needs. The techniques developed for mass-producing welded ships transformed shipbuilding permanently. The modular construction methods, the stress relief procedures, the understanding of brittle fracture, all became standard practice in post-war shipbuilding worldwide. Bessie Hamill returned to civilian life in 1946 without fanfare or public recognition. She never received a medal. She never testified before Congress. She never saw her name in the technical papers that later documented the welding revolution she had sparked. The engineering establishment absorbed her insights, repackaged them in mathematical language and academic terminology, and published them as if the discoveries had emerged from laboratory research rather than a night shift welder's practical observations. For decades, welding textbooks taught stress relief sequencing without mentioning the woman who first recognized its necessity, while watching hull plates warp under her torch. Yet, her legacy permeates every welded structure built today, every pipeline crossing frozen terrain, every pressure vessel containing dangerous forces, every bridge spanning rivers, every modern ship sailing the oceans, all carry her legacy in their sequenced welds and stress-relieved joints. The American Welding Society's Structural Welding Code, first published in 1947, codified center-outward welding sequences and stress relief requirements as mandatory standards. Modern bridge construction inherited these principles. The catastrophic failure of the Point Pleasant Bridge in West Virginia in December 1967, which killed 46 people, included residual welding stress as a contributing factor. Post-disaster code revisions mandated the sequencing and inspection protocols that Victory ships had pioneered decades earlier. The Trans-Alaska Pipeline, 800 miles of welded steel carrying hot oil through sub-zero temperatures, exists because engineers understood the lessons Hamill taught. Every section of that pipeline was welded using procedures that explicitly referenced Victory ship methods to prevent cold weather cracking in Arctic conditions. Nuclear pressure vessels, the massive steel shells enclosing reactor cores under extreme temperatures and pressures, represent the ultimate application of stress relief welding. The entire vessel receives post-weld heat treatment in enormous ovens, eliminating residual stresses that could become failure initiation points. The engineers designing these procedures in the 1950s explicitly studied Victory ship construction as their foundational reference. The Liberty ship program's true achievement was not the 4-day construction record that made headlines. The real miracle was the willingness to stop, admit mistakes, listen to a frontline worker, and redesign an entire industrial system based on observed reality rather than established assumptions. That willingness to adapt, to prioritize what worked over what was supposed to work, saved the Battle of the Atlantic. By war's end, the combined American shipbuilding effort had delivered over 55 million tons of merchant shipping. German U-boats had sunk approximately 14 million tons of Allied shipping during the entire war. The replacement rate was 4-1. For every ship the U-boats destroyed, 4 new ships arrived to replace it. Admiral Dönitz's strategy of winning through tonnage warfare had been crushed by an industrial capacity he could not have imagined. The 2,710 Liberty ships, despite their flaws and failures, carried millions of tons of cargo that kept Britain fighting, supplied the Soviet Union through Arctic convoys, and built the logistics base for invasions across North Africa, Italy, and France. They were emergency vessels that served their purpose. Many survived the war and continued sailing into the 1960s, their structural weaknesses managed through careful operation and regular inspections. The 531 Victory ships represented the perfection of emergency shipbuilding, vessels that combined speed of construction with long-term reliability. Many Victory ships remained in active service into the 1970s, 3 decades after their construction. Some were converted to container ships in the 1960s, pioneers of the containerization revolution. The last Victory ship in commercial service, the SS Victory, was not retired until 1982, 37 years after her construction. Today, a handful of Liberty and Victory ships survive as museum vessels and memorials. The SS Jeremiah O'Brien, a Liberty ship launched in 1943, remains operational in San Francisco. The SS John W. Brown, another Liberty ship, operates from Baltimore. The SS Lane Victory, a Victory ship, is preserved in Los Angeles. These survivors stand as monuments to the workers who built them, the sailors who sailed them, and the industrial revolution that produced them in numbers the world had never seen. The story of how American shipyards built 2,710 Liberty ships, while Germany built 1,100 U-boats in 6 years, is not simply a story of industrial capacity. It is a story of adaptation, of recognizing failure, of listening to workers on the production line, of redesigning systems when they prove inadequate. It is a story of Bessie Hamill, a night shift welder who saw what engineers missed and had the courage to speak up. It is a story of Henry Kaiser, who bet his reputation on mass production and, when that production revealed fatal flaws, had the integrity to stop and fix them. The mathematics of the Battle of the Atlantic were ultimately decided not by tactical brilliance or technological superiority, but by welders learning to start in the center and work outward, by steel treated in ovens to relieve stress, by corners rounded to eliminate fracture initiation points. The unglamorous details of fabrication sequence and stress relief procedures saved the war at sea. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.